Hello everyone. This is Dr. Sriram, Assistant Professor, Department of ECE, SRM Institute of Science and Technology, Katangalatu. And here I'm going to teach you the cyber physical control system. And of course, in this course, you will explore the fundamentals of controller operation and standard how control systems automatically maintain the desired performances through feedback, and we also will learn the various control methods such as on-off control, proportional control, integral control, and PID control, along with their applications in thermal and pneumatic systems, which are all mostly used in that industry applications. So let us see a small introduction about what is meant by control system. So you know that the physical control system, it is a combination of sensor, controllers, actuators, and feedback mechanisms used to monitor and regulate physical process automatically. It forms the foundation of modern automated system used in the industries such as robotics and automated system, biomedical devices, thermal systems, pneumatic systems, and radars. So the main purpose of this control system is to design the system performance and to reduce the human interventions, and which obviously increases the accuracy, reliability, efficiency, and it also enables the automatic decision making function through the feedback controller. So there are so many examples are there which has been available. So here a few examples that has been listed. That is temperature control in air conditions, speed control of the motors, then industrial automation system and smart manufacturing systems. And in this model, we are going to learn about the fundamentals of controller operation and closed loop control system, and what are the different types of control modes are there. And there are five different kind of control modes are there. And we also bring that concepts of what is meant by error control and how we got to set the set point and what's the purpose of the feedback control. Based on the feedback control, how this control is going to take the action and its output. And besides, we also note the differences between the proportional gain and the proportional band and time proportional control and its duty cycle calculation. And there are few applications on the side of the control system. There are two applications that has been listed and that we are going to see it. One of the applications is the thermal system and also heat transfer systems. First, let us see the controller operations. The controller is an element of the closed loop system that process the information needed to perform the decision making process. And this also we consider the brain of the system because that automates the system performance without the intervention of the human. So the input signal which is applied to this controller is an error signal. The input signal which is applied to this controller is an error signal, and which is the proportional to the differences between the desired set point and the feedback point. So now the controller takes an action and that changes its that make a changes which is needed in the control variables that need to be compensated for the disturbances that upset the process or changes the input set point. So now the controller responds to these changes by producing an output signal that derives the actuator to alter the controlled variable until the error signal is reduced towards zero. So here we can find there is a controller, we have a set point and feedback signal. So usually we found the error signal is nothing but the differences between the set point and the feedback controller. As we are represented, it's the error output is x of t because with respect to each and every time second, the error signal is being produced. So there are different kind of modes of operation that are available, and one of the operations called as on-off control modes. Another is a proportional control modes and integral control modes and derivative control modes. So these all the modes that has been selected by the design engineer, which has been determined by the requirement of the process that will be dependent on the process. Now let us see one by one the modes of controller of operation. The first controller operation is the on-off controller. So this on-off control is widely used where the control variable changes very slowly. For example, if you take the temperature of large mass is very difficult to rise or and it reduces very slowly. So here, because of that time lags in the control loop, which is being unavoidable. So this type of control mode often used for slow acting operation, and that is the one that provides the on-off action. So this kind of action that controls the final control element that has two functions or two conditions. One is the fully on, another is the fully off conditions. So one example is the refrigerator unit. So here you can see the controller compares the temperature to the set point. When the temperature increases above the set point, the controller turns the compressor on, or if the temperature reduces below the set point, the temperature is off then. So the controller variable cycles above and below the set point. As here you can see the figure. So when there is a controller is above the set point, it is off, and below the set point, it is completely on. So one of the drawbacks of this on-off system is that the rate at which the final control element switches on and off, which will be very, very high. So this condition can result in excessive wear to the equipment. Another one is that proportional control heating systems. So in the proportional control heating system, there are some situations that require. One is the tighter control of the process variable than on-off control can provide. And this proportional control provides the better control because its output operates linearly anywhere between the fully on and fully off. As its name implies that its output changes proportional to the input error signal. The greater the error, the more the output responses. So in this figure, what we find, to obtain this type of control, there are two modifications that need to be done in the on-off system. So first, in the on-off switch, the thermostat is being replaced in the bridge network, and the output of this bridge network produces the variable change output, and that has been given to this circuit. So here in the solenoid type of fuel valve, the fragments must be replaced with a proportional valve. So the proportional valve opens proportionally to the input voltage from the applied from the bridge, and the larger the voltage, the more fuel is supplied, so that the higher temperature is produced. So controller amplification, it is nothing but it has the capability of amplifying the amount at which its output changes in proportional to the change applied to its input. Amplification by the proportional controller is referred to either proportional gain or the proportional band. The proportional gain is nothing but it is the change in output to change in input, and it is mathematically described by the formula gain is equal to percentage of output change divided by percentage of input change. Proportional band, it is also the amplification. It's also expressed in terms of proportional band, and it is in the shortcut term, it is called as PB. It is defined as the percentage change in the controlled variable that causes the final control element to go through 100% of its range. So mathematically, it is represented like this. That's PB is equal to controlled variable percentage change divided by final control element percentage change. So there is a relation between the proportional band and the gain. Both are inversely proportional. As well as we have a larger band, gain will be reduced, and we cannot get the larger gain. If the gain is much, much higher, the band will be much, much lesser. The next important control mode is the PIC, that is proportional integral control. So the purpose of this is that suppose any controller you may take which has some inbuilt natural error or that may deviate from the existing system. So the integral mode of control is to designed to eliminate the offset inherent. This offset inherent is that was said the every control system may have its own natural error. So that is in proportional to the controller, and it develops a control signal that depends on the absolute value of the offset. The integral mode does not function by itself. Instead, it is also used along with the proportional control mode in the controlization of the closed loop systems. So there is a figure which has been seen over here. See in this figure, if you see, there's a same circuitry that we have used as the proportional controller with an additional amplifier that performs the integral action. So the second op-amp is called as the integrator here. At first instant, a DC voltage is applied to its input, and the capacitor starts to operate like a short circuit. Recalling that the gain of the inverting op-amp is dependent on the ratio of the feedback resistance, and the input resistance is. So we find the gain is equal to feedback resistor divided by input resistor, along with the how much voltage that is being applied over there. So this graph shows that compares the input voltage with respect to its output voltage, because as we are seeing the integrator, and at time t is equal to t1, the capacitor starts its charging its voltage applied to say in non-inverting output, and when it reaches that maximum voltage, then the non-inverting terminal, its output voltage is inverted and it start to increase in the negative angle, in the negative direction till the duration t2. Another one controller mode is the time proportional controller. It is also called as the pulse width modulation because that controls an actuator by switching the output fully on or fully off by varying the periods of time. So here the average power that can be delivered to the load is controlled by changing the duty cycle. A common method for controlling a DC voltage actuator device, such as heating element or DC motor, is to vary the DC voltage of an amplifier that drives it. So this method is called the proportional mode because the magnitude at which the actuator is driven is proportional to the amplitude of the applied voltage. For example, by doubling the applied voltage produced by an amplifier, the temperature of the heating system is doubled if the gain value is 1. Another way of controlling the actuator is to use that time proportionality, that is called as the pulse width modulation. So the time proportioning is a method in which the amplifier output is switched alternatively on and off. Changing the ratio of signal on to signal off varies the average voltage produced. So here there is a graph is given. So if you look at the square wave is set as plus 10 voltage. When the amplifier is on, and 0 voltage when the amplifier is off. The ratio of the time the square wave is on is to the total time period of one cycle is called as the duty cycle. So if the duty cycle is 25%, we'll have the 25% on time and remaining 75% is the off time. Time proportionality in circuit. So it is an electronic control circuit that regulates the average power delivered to the load by switching the output fully on or fully off for varying time intervals. So the amount of power supplied is the load by switching the output fully on, fully off for the variable varying the time intervals. So here the amount of power supplied is controlled by changing the duty cycle on and off the cycle time ratio. So here you can find we have the two inputs. One is the inverting input and it's a non-inverting input. Where non-inverting input is compared with the threshold voltage, where non-inverting input is controlled with the threshold voltage. Where inverting input we are having a supplied voltage. So whenever we find the non-inverting output is less than the inverting output, and we'll have the output is 0. Whenever the inverting and non-inverting inputs are same, and that produces the output which is equal to that negative voltage. So when the non-inverting output is greater than the inverting output, obviously we'll get the positive voltage here. And next one is the thermal systems. So many products that has been manufactured today are the result of process that inverts the temperature control. So higher temperatures may be used to soften the metals before they are framed into a desired shape or to melt plastic in an injection molding machine. Low temperatures are necessary to preserve dairy products in the food processing industry. Obviously, the manufacturing process that are also affected by the temperature are referred to as the thermal systems. So here one of the examples that has been taken into consideration, that is the thermodynamic heat transfer system. So here the transmission path of the thermodynamic transfer can be made through materials that are solid, liquids, gas or a vacuum. The process by which the heat is transferred by a solid is called as conduction. And here you can see the figure. There is one of the example for the conduction. One end of the metal bar is being placed over an open flame heat sources, and the molecules over the flame which moves very rapidly. So the increased molecular velocity causes the collision with the neighboring molecules, which in turn causes them to move very quickly. So this action continues until the molecular movement throughout the bar has increased. The best solid material thermal conductors are metals. Some types of non-metal solids are